All right, let's do a general review so far. Chapter 1, descriptive statistics, inferential parameters, remember? So we have this whole category over here that's called sample statistics. And its equivalent, instead of calling it population statistics, they're called parameters. That's the whole group. So can somebody tell me what is the best estimator of mu? What is the best estimator? Huh? Yeah. It's sample average. We will be. So what happens here is that we've calculated this from x1, comma, x2, comma, dot, 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 comma, x sub n, little n, the nth term, right? We have to name, we give a name for every observation. We call it x1, x2, x, or whatever letter you want to call it. Okay? These guys were taken out of the thing that we can't grasp. And where we can't grasp, then we take unbiased sample, right? And then this unbiased may have been x1 here, x2, x3, and dot, dot, dot to x of n. Or actually, this is x to capital N, right? We normally expect this to be a lot bigger, capital N, than little n, yes? Because it's a subset. So this is capital N. It's the population size. Okay? And what's the best estimator for this? This is called the population deviation. Standard deviation is going to be the best estimator, and that's going to be S. S is going to be the best unbiased estimator of this, and this is going to be the best unbiased estimator of this. And now we had a new guy. He's called P hat. Okay, P hat is a sample, as you might guess, a sample proportion. Okay? Now, I'll tell you why it's important here in a second. But it turns out it has this thing that looks like P. It's kind of what we call a rho in Greek. And so this is going to be the best predictor of this, which we're going to call this our population what? Proportion. And a proportion is simply a fraction, like A over B, where B cannot be equal to 0. Okay, that's the only thing. But what I'm saying is that often is the time when you're trying to make a prediction about a population and you want to know, you want to get an estimate of the average. Well, this is it, X bar. If you want to get an estimate of how it's deviating away from the average, how the pile is doing, well, then you want S for this. But the question might be not what the average is or the deviation, but a certain proportion. Let's say any number you can think of, 3 out of 5. There's chances that you're going to die by the time you're 50, let's say. It's morbid. All right. What I'm saying is that's a ratio, right? And I might see if the data supports that ratio. That is a proportion. You see why it's important? Because we're not just going to ask about God's average and not just about the deviation. We might ask, so what is the chances or what's the probability or of some ratio? Even a percentage is like a ratio, right? You're going to have some percentage is probably going to be something over something, or even velocity, for example, is a ratio. It's distance over time. Okay, so my point is this is going to be another powerful, this is the true proportion known in the population. Did somebody else think of a possible proportion? I can't see in the dark, so it's okay. I'll pick you by your eyes. Anybody think of some kind of something you'd like to know, a proportion? Something not necessarily the average of a population, but come up with some story where you'd like to know something about the big picture, but not necessarily its average. any kind of ratio, any fraction, like so if I say I believe that 2% of the American population, say, suffer from some really weird genetic disease, let's say. Okay? 2% is where did I get it? I'm saying I think 2 out of the whole population, right? Do you see that that's 2 divided by the sample size or whatever? You're getting an estimate. I'm saying I think that the truth is that 2% of the population suffers from some genetic disease. Okay, and now I want to see if my sample supports it. That hypothesis, you understand? This is probably going to be used more than the average even. Not necessarily. You follow me? It's an important point, and this is called a proportion, and you'll get into it. And of course, you know, this is going to be the sample proportion, right? And this is, we have our equivalent, because this is everything sample, deviation, sample, average, if you wish, population, average, right? And we have population what? Deviation. You can actually use P, you know, population average. And this is population proportion. Okay? Now, almost done. But now we want to see if we can find, I told you from the first day that what we're looking for is to see if this process is yielding some kind of underlying pattern of which we can take advantage of and make a hypothesis. This is a forecast, right? And one of them is we take this, right, and we look at it and we construct a frequencygram, which is, you know, in chapter 2. A frequencygram is simply, it's somewhat subjective because you usually pick the number of cells you want to see where this data is piling up on. Now you can bias it by putting too many cells, because then you'll have this like this and then it'll look like blank, 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 and then another, see what I'm saying? So you can stretch it or combine it or take it and make it kind of biased. But generally what you want to do is come up with these cells that are equal width, that are covering from your maximum, you know, so this is out of all of this, your maximum, the maximum value, I don't know what it is, but x max minus x min, okay, divided by this, the number of cells you want. Okay? And that simply determines the width of each cell. Okay? That gives you general. Clearly, if you take the biggest and the small one, this is going to contain all the observations from the sample. Yeah, there's not going to be anybody left out. Right? There's not going to be anybody left out because I got the most extremes. And they're included. So whatever value you have from minimum, I don't know, I could go any number, 0 to 10, and 10 to 20, let's say, and 30, and 30 to 40. Now, there are different schemes that I'll leave to you, but they can put a little margin in between with maybe add a 0.5, depending on what these numbers are, right? So that you would go from here to 10.5. The reason you extend a little bit is because sometimes there's an argument that where does 10 go? Because if they were really, you know, if they're continuous, then 10, you could say, well, 10 is the start of this one, or it's, you know, which cell do you throw it into? So by putting these little gaps in there, you make sure that this one cell, right, that everybody will fall in some cell, and nobody will stuck in the middle, that's all. Anyhow, all you simply do is, remember this sample, right? This sample is a subset of the population, right? Yes? Okay. Now, we're looking for the structure of the data itself by how it's piling up on these cells. So, I'm simply going to count them as tallies, as stick figures. You know, and I'm going to see out of this, I'm just making it up now, but let's say I have 1 and 2 fell here, and let's say 5 here and 3 here, for example. That's a tally, that's a frequency graph right there. Because you're finding that each one of these is a frequency. right? And each cell has this added frequency of 1, 2, 3, and so forth, all right? Somebody say okay? All right, so now, if I come back over here, and let me erase some stuff. Give me some room here. This is chapter 2 stuff, and then we start chapter 3 and chapter 4. This is, we're going to put a vertical axis, and we're not going to change anything, and we're going to do it twice. Okay, I'm going to do it like this. Okay? This count here is simply counting like this. For example, it's counting the tallies. So you would just have something like this, where you have simply the counts of the tally. 1, 2, 3, 4, 5. See? That's all you've done. And now all you do is make a box corresponding to one tick mark because there's one tally. And so forth. And so forth to 5. And then again to 3. You understand? Now we have a frequency graph, bar graph. Okay? And all of this, everything that we use over here is descriptive statistics to make inferential predictions of these. By the way, all of these are parameters as a group. Okay, now I'm going to just put another vertical right here and have it extend so that it can be switched with the other vertical. And in that case, look what happens here. Now, suppose I take the summation of all the frequencies f sub I, where I equals 1, right, to the number of cells that there are. 1, 2, 3, how many ever cells you have. This is telling you to add the frequencies in each cell till you get to this cell here, right? This is the number of cells. However you chose the number of cells, remember, from the maximum to minimum divided. However you chose the number of cells, all of this summation from I equals 1 to the total number of cells is simply asking you to add all your tallies. Can somebody tell me what that equals? If I add up all my tallies. No, I don't want a number. I'm talking theoretically. Well, that's 1, then you'd be done. But there's another count, 2, 3, that's not correct. I mean, unless you only had one observation. I have to count all my tallies. That's all it's doing me. Huh? That's right, sample size, n. Clearly, the number of tick marks is in fact the sample size. All this means is what? Take f of 1. F of 1 in this case is 1. And it asks, have we finished the total number of cells? No. This generates a plus sign. F sub 2. See it? And it says, have we done? No, we don't know. In our case, we're going to go plus. Dot, dot, dot means think inductively. It's following the same pattern, right? Until finally we're going to add up our f sub, whatever it is, f sub cell. Number of cells, let me put. And it's a little messy, but that's all it's saying, is that if you sum up all of the tallies, it better equal to n, which is the number of observations. Easy enough? Okay, now I'm back to this vertical, so this makes for a histogram. Okay, which I want you to note, my definition of it is going to be sample, as always, and this is going to be distribution. Okay, distribution, okay, not deviation. I'm not talking about deviation. See, I'm talking about the way things are distributed. Yeah? There's distribution and there's deviation. They're different. Deviation is if you have, okay, well, let me just finish this part and you'll see. So now, in order to get the histograms, you have to change these numbers to this. you take 1 and you divide it by the sum of the frequencies, which is n. You take 2 and you divide by the total number of observations. 3, the n, and there's no difference in the drawing. All I'm doing is taking each one of these points, dividing by n, representing probabilities. Now we enter chapter 4, and we start hitting probability theory. Do you follow this? So all I'm doing is changing this to this. Now, they call this, when you change it from a frequency count to an individual count divided by the sample size, then that axis, and that is called our histogram, which I want you to post and write down. Make sure you got it. Sample distribution, okay? And we're going to have a population, believe it or not, distribution. And usually it's a lot more, it's not so step, because we got many, many more observations. So if you could put it together, more than likely the graph will be kind of smooth, or what we call continuous. Okay, it's continuous because I never lifted my pen up. So there you have it. Now, this shape I inferred from this shape. Again, this is my description. This is my inferential of how the true pattern is distributed. This is the whole course. Because what happens next is that we take this man-made thing plus an error term, right? And we're going to put plus this error term and minus this error term in parentheses with a certain probability. So we're going to put boundaries made by man stuff around what we consider to be God's truth. That's bold. That's probability and statistics, is making that assertion that the mathematics is allowing us to put boundaries around these parameters of only known to, I'm using quotes, God. I mean, how dare we? But we can, with a certain probability. And you'll never say, I know this is true to be 100%. It will never happen in statistics. There's nothing 100% in that sense. Okay? You can only, because it has a probabilistic nature to it. So you can only put a boundary around it. Okay? Obviously, if you're getting tighter and tighter on the boundary, right, you expect the probability is going to go down of containing God's truth, right? Because you're minimizing. If you got a really wide bandwidth around it, yes, there's a good chance it contains God's truth, right? So you go up to 95%. When you hear election forecasts, well, so-and-so appears to be winning, right? They'll say, this person's got so many percents, that's a proportion. And they'll always say, this guy's leading, you should listen, and they'll say something like plus and minus 3. They just gave you an interval. And they don't tell you, but they calculate it at a 95% confidence. Unless you go hire Cambridge Analytica, then they upset the whole system. But any questions in this thing? I know I'm pounding it into, but I'm actually going to cover all 4 chapters now, going this route, right? Because this was the descriptive right here, that these sample statistics predict these parameters. We are going to use them, right? That's really the core of it. The rest of it is, there's different types of data, categorical data. I'll leave that to you. That's boring. To me, it's more of the concept stuff of it. Okay, next is how to see how this thing is distributed after you've calculated these morsels. Now, with regard to deviation, if in fact the distribution is like that, then in case it's a symmetric distribution, do you see? There's just as much area under this side as that side, and this thing, the average always lands with a bell curve, a Gaussian curve, normal curve, all of those same names. Okay? But what the deviation does is give you some measure of this. It gives you a measure of how fast, so to speak, this is spreading away. How fast that this thing is, stretching out. So you would have, let's say, call this deviation S1. But you have S1 going this way and S1 going this way too. Okay? So I want you to compare that with this. There's another distribution, but it's a bell curve too. Again, right down there would be X bar. If this was physics, they call it the center of mass. The center of mass in this case would be right there. That thing would, if that was cut out by cardboard, it would be the center of mass, where you could balance it. Now, if you take a look at this S, right? It's a lot. I call that S. Let's call it S2. I would expect S2, right, to be a lot less than S1. S1 should be a greater deviation than S2 by looking at it pictorially. Do you see? That describes the way that this thing is spreading out. Okay, now one thing that I'll cover, so might as well cover it now, is they have this thing called the median, the mode, right, and you have the average, of course. So what we do is that in many instances, you're not going to hear on the news talking about the average. You're going to hear the median. Does anybody know why? You'll hear like the median price of a home in California, say $530,000. It's the middle, and what's wrong with using the average? Could be lower. Why? Your final pieces of data, you could have things called outliers, right? So you could have somebody that just their price that they paid for that house is so far out, it's in the millions, right? Hundreds of millions, let's say, like a yacht. Some of those are like over 100 million. If you could spend that much on a boat, right? you got a pretty nice life, I guess. It's nothing. What else is there? But anyhow, that's the key here with this. So there's a rule of thumb. And I'll pull that up in the book. But with regards to the central tendencies, we have the measurement of, well, obviously, we have the sample average. This is a central tendency, okay? And then we have the median. And it's just a median is another measure of tendency. And then we have mode. Okay, and so anyhow, we know that this is a summation of all the observations divided by the total sample size. We know median now, you have to line them up. So whatever you have, x1 has to be lined up so that it's smaller than x sub 2, that's smaller than x sub 3, right, with this pattern continuing to the x sub n. Okay, you have to do that first. And I'm talking that this is the smallest of all of them. So just put them in order. Okay, so if I have an odd number then, 1, 2, 3, 4, 5, there really isn't any confusion because the median is going to be the geometric center of that number line, so to speak. So you just take your arrow and go to here, and you take your arrow and go to here. Where they meet, that's the median. Why is it helpful? Well, sometimes this guy might have been not 5, but 5 million. So the average is going to skew way over. It's not really going to be all that helpful because you have this freak outlier. This one doesn't care. It's invariant. You could call it 50 million. It's still going to go to the middle. Yeah? And then, well, the case was if you have just 4, then you have 1, 2, 3, 4, for example. Again, but this time you got to go to the center of the 2 only because there are an even number of observations. Are we okay with that? Okay, if they're an even number, then in this case it's going to be the average, or 2.5 would be the median. I get it out of the way. The other thing is the mode. So if you have something like this kind of x sub 1, let's see, 2, 2, 5, and then 3. In this case, the mode is going to be just the highest frequency, in this case 3. It's just whatever observation repeated the most, highest in frequency. Okay? Okay, with regards to organization, there's something called a box plot, box and whiskers. That is just another way of describing it, and a distribution of sorts. So you're going to have these whiskers, that's called a whisker, and then you're going to have, this is the distribution, and you're going to see somewhere around there, let's say where the average hitting, right? And this is going to be the other whisker. So what happens is you have like an X bar here. The difference could be some sort of deviation. And this is your X minimum, and this is your outlying X max. So it gives you a feel of these outliers if they're in there. It's called a box plot. Okay, there are different plots that you can do. It's really easy to do it in Math Crunch. You can tell me how to do it on the TI 84 plus. I gotta relearn that because I haven't used calculators in a long time. But I teach out at the prison. We can't use computers apparently, so I have to learn calculator again. It's not bad, but it's a little bit awkward compared to using software, especially when it loads it right in without you even having to enter the data. Okay, now let's go back to the book then. Unless there's any questions, generally there's a test for normality, and basically if the data lines up on this line, I'll show you that too. Let me just show it to you. It's a normality test. I don't think it's worth all that much time, but it's another way to say, if I look how it stacks up, I can see it's kind of bell curve right. This is another test. And now let's go to, it's called the rule of thumb. And that one's going to be on page, well, let me go to 57 just to cover what I finished saying. So let's go back. Let's see, where did I put everything's black here. Okay. There we go. Okay. Let me open up the textbook and see how it works out. Okay. Oh, I think I could do it here. Okay. There's all sorts of course, there's endless ways of displaying the data. But this thing's called a normal quartile quote and plot. And it looks a little bit like this. So it'll generate this line, okay, and then it'll plot the data points according to X values and Z scores. I'll get to that later. But the idea is that if they kind of line up along the line, that's another test of normality of the data, how it's distributed. Okay? That's all that I really wanted to say about that because they throw it in there. Okay, now let's go over to, you have something that's called a scatter plot too. I won't worry about that. Okay, that's 89. Let's see if I got it here. Okay. Now, well, I might as well. This if you recall, that we have an equation for, I'm stepping back a little bit. This is another equation that you'll kind of come across, which is, I think, number 2 on your cheat sheet. This equation is another way of calculating the average. Now, why, anybody tell me why we might want to calculate the average this way, and instead of adding up all the observations and dividing by n? Yeah? To save time? That may be. But the idea is this. You're going to use this when you don't have the raw data. What you have is the frequency data. So what you have in this case is this. So look, if I give you this, and I give you some tallies in between, right? Okay, something like this, yes? Can you tell me from here, I know that something fell in between here, A and B, right? But can you tell me what the actual number was for that tally? You can't. We lost something now because they gave us purely frequency graph. Okay? So what this is for is to calculate the average when you have a situation that you have just the frequency graph. You got it? And what does this mean? Remember, Fi is going to be changing for however many number of cells. So you're going to be taking X. We don't know what X is, right? I just got through. We don't actually know what the data is, right? We know how grouped. Well, what they do here is they take, for X, they call it the X midpoint. Of course, each one has a midpoint. So when I says X, they're just telling you get the number, the average of this and this. Do you understand that? Does that make sense? What it's saying is that take your frequency, let's say in the first, let's say I equals 1. So F of 1, you see, is going to be 1. And what's X? Well, we don't know what X is, so we're going to use the average of the cell. This is going to be, let's say, 1 to 2, right? What we'll use instead of the real data is we're going to use 1.5. So you're going to go to the next one, F of 2. You're going to multiply it. By the way, what does that equal to? Don't tell me 50, I know. But what does the sum of all your frequencies? No, I don't want a number. Again, in theory, what will this add up to? Nope, no deviation. That's average. Yes, the sample size. This is counting up every single tally. The tally has to add up to n. I know it's confusing because I got numbers too, but I'm saying in general, I have no numbers here. You know, what it really means is to count from I equals 1 to the number of cells that there are. And instead of individual data points, you're using the midpoint of each. So you have midpoints of this times that, plus midpoints of this times that, plus the midpoint here times that, plus, you understand? Now, you hit the last cell, you add them all together. That, in this case, would be this number. And this is n. I keep trying, when you see this, that exactly is the number of, right? We counted everybody. I asked you this earlier about what does summing up all your tallies. So in the end, that's all that means. Okay? It's another way of calculating the average when you have frequencies. Okay? All right. Let's go through that because I hate when it does that. It likes to hit on there sometimes. Okay. So this is a weighted average, which I don't want you to waste too much time. This is the same as the average, but you can weight some, like supposing I'm adding your test scores, but I want to say some tests are more important than others. Then I can weight the average stronger towards whatever test I think was most valid. You understand? That's a weighted average. These are details that I'm sure you can learn. in no time. Okay. Here is exactly the steps that you're supposed to go depending on how you want to solve this. Whether you want to use Excel or the TI-84 Plus, it's supposed to give you some information on how to do it. StatCrunch is what comes automatically. Okay, we might as well talk about this quartile business too. You've seen quartile 1, quartile 3. Let's just get that over with again. Right now, if you were to, like in the case of the median, and you're gonna order from smallest to biggest, right? The data, and then what you want to do is just simply. Okay, so suppose I have one. Well, so you got 1, 2. Let's say so 3, 4, I don't know, let's say 5, so 5, 6. So what you're going to do is, let's see, 7, 8. You're just going to split it in quartiles. So you got to go in fourths. So you'll be cutting it, let's see, so we got 1, 2, 3, 4, let's say 1, 2, 3, 4, right? So this guy is called the first quartile. Second quartile. Anybody know what else that means? Equals the second quartile? Half. Yeah. It means it's also equals the median. Not the average. The median, right? Remember when we came in from two directions? Does anybody remember that? Okay, and of course this is the third quartile. You can build your box plot based on those quartiles. That's all that quartiles are. Okay, anyway, I was through that. So, remember that I told you that we have something called the range, which was simply the maximum data point minus the minimum, right? That's the range. Later on, I divided it by however many cells to get the cell width. So, I mean, it's easy to calculate, right? Okay. This is what we've used to, where you have the sample, every observation, you're going to subtract the average, square that difference, and then add them all up. This way you'll never get a negative. Then you're going to divide by n minus 1, and because this is squared, to get back to just this, we have to square root it. That undoes the square. Are we all okay with square roots, or do you need it going over? How are square roots? Do we need a brushing up on roots? Yes or no? Oh, that mean yes? Okay. Well, anyway, it's just if you have a good grasp of it, then I guess. Anyhow, I can actually expand this algebraically and derive this. Okay, why do some people want this as preferred to that? If you notice here, in this one, you notice how we didn't have to calculate the sample average. It's in there, but it's hidden. See that extra n? This is another way of writing, these are equal ways of calculating the sample deviation. This might be easier. It says take every observation, square it, and then add them together. And then multiply it times n. Then, be careful, this says take your total summation and then square it. See, it's outside the parentheses. And then finally, n times n minus 1. Okay, they're equivalent. Of course, when we talk about probability and actual deviation, we don't have a concept for negative probability or negative deviation. That would be like antimatter. Okay, so all right, we already did that. That we've done many times. Yeah, here's the data, and that's all you do. That's all that means. Sum up all your data and divide by the number of things. That's it. Okay, and then it's all right, and then same idea here. These are the differences squared, and then you take the square root after dividing by that. Okay, let's see. All right, this is the rule of thumb. You're going to see it in homework, so I might as well put it on your thumb now while you got it, okay? So this is a rule of thumb for identifying significant values. So we're going to use as a rule of thumb, look, if you take God's average and subtract 2 deviation, population, right? We'll call that, anything lower than that, we're going to call significantly low. And anything of mu plus 2 sigma, lowercase sigma, is going to be considered what we call significantly high values. So if we look at here, it says, and we do our graph, and this is the way the stuff is stacked. Okay, so here we have the rule of thumb. Depending on where, we'll have a test statistic land somewhere in here, but wherever it lands, you see how this, there's a boundary right here, see it? And so these, anything higher on this side, we're going to label as high. And then here's a rule of estimating a standard deviation. This is a rough rule, right? Instead of doing this, each observation, subtracting its mean, squaring it, dividing by n minus 1 and then taking the square root, all they're saying is take the range. What's the range? The maximum minus the minimum value, and divide by 4. That's pretty rough rule of thumb. But when in a pinch, take your reign. Okay. So anyway, you'll see the next rule will probably is better than this rule as far as more general. Okay. So here's an example of your, calculating your deviation. These two are nice if you ever want to see a video of how that works. Notice what this is. Population deviation, correct? Its equivalent looks like this. Its equivalent, what we're going to use to estimate it is x bar, correct? And look at how that looks. Okay, so that's the summation of all the little observations divided by little n. Okay, that's x bar. And notice that our average and our deviation. So what do we use to estimate this? What descriptive statistics do we use to describe that parameter? Sample deviation is correct. Now, I just want to look. This is the population deviation. Do you see it? This is the population deviation. Oh, yes? The sample deviation was this. What I want to point out is, look, I'm taking every observation and I'm subtracting x bar because that's from our sample, yes? Is that right? Yeah. And then that could be negative because it's an average, and then I'm going to divide by n minus 1. I want to call to your attention that this is every observation subtracted x bar. Not here. It's every observation in the population subtract the theoretical average. Because we're in, you understand? What I want to point out is, why are they using x bar here? Because this is all a creation from the sample. You need everything in the sample, but this is back to the population, and it needs to subtract its true average from each observation. Is that okay? How are we doing on time? I can't see. Oh, that's like, I can cover 3 or 4 chapters. Huh? Okay, let's try it. Okay. Okay, now this is something you just should commit to memory, all right? It's just, if S is called the sample deviation, true? Okay. You got to know that this is the same, but if you square it, that's going to be the sample variance. It's the same number, squared or not. So to go from here to here, you're going to have to take square root to get back. Remember, this has this stuff square rooted. If you square both sides, you get rid of the square root, but that's just simply that if it's squared, it's no longer called, it's the square of the standard deviation. We call that variance. On the population size, if you have the population, then we call that the population variance. It's nothing more but the squared of the deviations. So if I say variance, don't freak out. It just means the square of the deviation. So here it is. It's listed for you. Is the print big enough for you to see? There in the back? Huh?
It's not big enough.
Oh. Well, you should let me know. Is he okay? Sorry about that. Well, you could learn some. I'm going to record this, put it on Canvas so you can blow it up. I don't know. Anyway, I just write sample deviation, sample variance. Standard deviation, population deviation, that's it. It's just a way to call things. You mean you want to do an example of a problem?
Yeah.
Oh, well, you have to call it out. I can't really.
Let's do one.
All right, which one?
Let's get the cross up.
Which one?
I don't know.
Okay, well, try to formulate an actual question, and then that's a little vague. Okay, we'll run across an example then if that's what you wish. Okay, don't worry about this. Instead of square root, they're taking the absolute value. So notice that we don't have a square root anymore. Okay, but if we can do an actual problem, let's do that. Would you tell me what chapter you'd like to see a problem on? Okay, thanks. 3.2. That's in the book or in the computer? Okay, so it's here. Let me see. Okay, so that actually the one I said don't worry about. That's the one you had to worry about. So you have the population. I don't think I can make it. Can I make it any bigger? Okay. Yeah, it's bigger, but the size didn't change. Anyhow, so let the population consist of 10 cigarettes and 11 and 21 cigarettes smoked in a day. So show that sample size 2 are randomly selected with replacement. The samples have absolute deviation that do not center about the value of the absolute mean. What does this indicate about the sample mean and deviation used as an estimator for the deviation population? I don't think it's really too big a deal. Basically here it's just the difference, right? The absolute difference. So when you want, you're going to calculate a deviation with the absolute difference. So that's how you'd find it. So here in the, let me show you here. Okay, that was the. It's pretty big. Okay. So they want the last thing that I covered. Okay, there's the mean absolute deviation. I don't know if you've seen that or not. That was the last thing. Okay. So the general question they're going to ask is, what does this indicate about the sample mean absolute deviation being used as an estimator for the mean absolute deviation of the population? Oh, you mean in that case? Yeah. Then you'd have the equation, right? And what's the population size? 2. So if I remember on that equation, it was x minus x bar, the absolute value? Number 15? Okay. 9 out of 6. Oh, number 15. Oh, let me go. Wait a minute. You said number 15? What we have here is basically, what do we have here upside down? What is this called? this chart here. A frequency, well, we'll call it a frequency tally. Because we're not really graphing anything else other than tallying, but it's sort of upside down. Remember, I do my tick marks on the top? Okay, so right here, each x, in this case, I don't have the raw data, right? But I do have the midpoints. So the midpoints of every one of these things is going to be used for my x. Okay? So let's do it like this. Suppose you have x sub 1. Okay, x sub 1. And we're going to call it x sub 1 to be the midpoint of the first cell. What is it? Yes. We're going to go x sub 2 as the next midpoint. That's going to be, what is it? And then x sub 3. What is it? Okay, and then x number 4. And then x 5. What's that? Okay. I don't want to paste. Okay. Okay, so 50, we call that 51. How many do we have? 1, 2, 3, 4, 5. Okay, and f of 6, x of 6? Okay. And then x of 7. Okay. Now, so now I have this. Now my frequency, I'm going to have f of 1. Let me do that in a different color. Okay, also I have f of 1. Can you tell me what f of 1 is? Okay, f of 2. F of 3. F of 4. F of 6. Huh? 60? Okay. F. This is f of 7? And, oh no, that's f, I missed one. There's 1, 2, 3, 4, 5, 6, f of 7. Okay, so now we're ready to do the equation. In this case, what is n? What is n equal to, actual number? 7. Be careful, because now our sample size is just our frequencies, the number of cells. Okay? So, I mean, we have n is going to be the number of whatever that adds up to. Do you understand? You got to add these up. What's the total count? That's your n. So, I'm ready to do it. Okay, so let's say, okay, here we go. Now, I'm going to follow what it tells me to do. Everything is going to be over the square root. Okay? Now, my counter, yes, is going to go from I equals 1. So, it tells me to take f1, yes, multiply it times x1 squared. There's x1 squared. You see it? And keep doing that, f2, you see, times x2 squared, yes? Plus, you're going to do that until we get to our last cell, which is going to be the number of counts, right, in the last cell, f of n. In this case, it's 7, right? And you're going to multiply by x of n, which is really, we got them here already, which are the midpoints of all of these cells. So that's x of n, right? That quantity you add up. Sorry, so no, each one of these you square, okay? So there it is. That's the first one, okay? And out here, by the way, I'm going to have, I'm going to pull n all the way out to here. Because, well, I know I better not. I'll just leave it. I'll put an n out here. Okay, now I have another parentheses here, but anyhow, over here now I have the minus sign. Yes? Now I'm going to do this side. That's going to be in parentheses. What's the first guy? F of 1 again. Yes? Times x1. Do you see it? Plus f2 times x2. Yes? Somebody say yeah, even if you don't know what I'm doing. Okay, then you go like this. Dot, dot, dot. Yes? Plus, you're going to get to your final f of n, x of n. Yes? And now it says, add them all up and square this whole summation. You see it? That's what it's telling you to do. Not squaring it. You're squaring the summation of the whole answer. Got it? And now you will divide that by n times n minus 1. Okay? So what we have to do is for f1, we're going to put 1. 1 here and 1 there. And x are the midpoints, what we've labeled now, x1, x2, x3, which are the midpoints of the cell.
So pretty much you times x1 by x1.
Yeah?
And then you square that, or you make it to
Are you talking about here?
Yeah.
Here you square each time. See it? Inside, it's squared.
And then the second time.
The second time, no. You do the whole summation and then square it. Okay? Now, why do we do it this way? It's the same reason that I tried to explain why we can do this. Remember, we can find the sample average by doing what? The frequency. Do you remember we can do a sample average that's something like the summation of the frequency and x of I over the summation of the f of I? That's how we did it using a frequency to calculate an average. Guess what this equals down at the bottom? What's the summation of all our tallies? Third time, sample size, n, right? Because it's the sum of all our tallies. Does that answer your question? Okay, who else got a question about a particular? You had one. Huh? Oh, you want to actually do the mechanics? Well, okay, if you want to do it, then let's do it. But you're going to need somebody wants to be handy on the calculator. We can do it, or however else you want to do it. You could actually.
I thought this program did it for you.
Yeah, but the thing is, we don't have actual data, the actual raw data, do we? We just have the tallies of each category.
You told us if we bought this website, we don't have to use a calculator.
Well, if you don't have to use a calculator, but for me to show it to you right now, I do. I would have to put in the numbers unless you want to see if it actually works. All right. But the actual thing is just accounting. So plug in a number and multiply. If you don't know how, ask me for help. I'll tell you what it means. It means take that times that, and that times that, that times that. I want you to notice that this means do the whole summation first before squaring that quantity. This has got the x on the inside. Did you have a question, a specific question? Oh, okay, you just had a general question?
Yeah.
All right. Is that it?
We'll be done for today.
I don't know, are you? You want to be?
I think everybody just.
The way I would solve this one, using the program, once you have this set up, right, you can look at this as just a regular average or regular deviation. And once you get it set up.